To be cognizant of that, how that simplification impact your conclusion. And I just got so worked up, and still am, about continuing to honor the tradition that Sam established for those. You know, to a certain extent, some people in the department thought he was all cut and tried, but they just didn't understand Sam's method of thinking about things. And when you talked to Sam, you discovered that he really had a much deeper understanding than those individuals attributed to him. And it's just incredible that he could...
Well, working in this community, one of the things, in the cryogenic community, I never met Sam, but you walk through the community, and particularly those of Joe's generation, there's also reverence that you hear from these people. You know, they talk about it, you know, and they just like Sam Collins, you know, and you kind of get this feeling from it. And I mean, it's one of those things that still pervades. I mean, you end up, you know, into my generation, you start, you know, there's certain standards, okay? There's certain standards, and certainly on helium liquefiers on par with the one you saw, you know, that's the standard, is that cycle. It is something, it is a technology that has held up now for 30, 40, 50 years. And they haven't improved, you know, I mean, there have been improvements, there have been differences, changes, people put turbines on them and all, but the essential idea, that's it. As I said, I mentioned, we have a project with NASA where what we are doing is adapting that cycle to over into a cryocooler that would be, you know, basically set up in orbit to keep things cool. There, you can't plug into the wall for electricity. You need a very, very efficient machine. And the Collins machine, I mean, that's what we sold. You know, we sat there and wrote the proposal. It's like, Collins machine, high efficiency, you know, and we're modifying it so that it fits this thing better, but that's the story. So the legacy continues. There's no doubt about it. I'm sorry, Joe.
Yeah, well, you know, and I sort of have dedicated myself to trying to propagate the tradition of Sam, and to see that people that follow his method of converting beautiful ideas to reality and hardware continues. And you know, you get word a little bit about the younger generation. You just put it in the computer, and if it doesn't work right, you just push the reset button.
Isn't that the way you do it?
You know, it's sort of like driving automobiles. I don't know, safety these days. So many of the young people don't have any perception of what hazard really is, because all the hazards that they dealt with, when they get into trouble, they just push the reset button, and then they can start over.
But the laboratory itself has very much, I think you've seen, is very much of a hands-on kind of thing, you know, it's building. And it may not be pretty, but it's just got to work. And there's, you know, there's a fair amount, but there's a sort of yin and yang here too, because, you know, for example, computers have done a great deal to be able to model and predict what things are and look at what the consequences are of this design decision versus the other. But ultimately, the tradition, at least in that laboratory, is ultimately you got to build it. I mean, I had one student, way back, we were doing superfluid Stirling machines that the coldest Stirling engines in the world, or Stirling refrigerators in the world, we cooled down to about 200 millikelvin, 0.2 Kelvin above absolute zero, 0.2 degrees C above absolute zero. And I had the student come in, he says, I've solved it, I've got everything and all. And he sat there and he came in and he shows me all these drawings, and he's got 80 kilograms, okay, so that's what, 150 pounds, 200 pounds of copper that has to go into this machine. And I looked at it and was like, how are you going to build that? You know, there's no way that you can support that kind of weight in a cryogenic environment. You know, it's like, And he basically, he went back a month later, he says, he came back in, he says, "I've got it." I said, "Okay, I hope it's lighter than it was before." He says, "It went on a big diet."
I had a friend who was an architect, and he talked about students doing plans for buildings, and that one of his older professors would always say, "It looks great, but will the water run off of the roof?"
Right.
That's the test.
Right.
Does it work?
Well, I just have spent a lot of time trying to ensure the propagation of the Sam College tradition, I guess, and to have family come and visit and say they are proud of the tradition that he has established gives me a little bit of reinforcement that maybe I wasn't just blowing my whistle all that time. Maybe there is really something here that we ought to think about how we have it evolve and develop and try to combine the assets that we've discovered in the last few years into a system that makes something that really works and gives us all benefits. I'm not sure he was the head of the chemistry department when Sam came, but anyway, he was the one that hired Sam. And Sam, I don't know, I never really completely, but I think it was from his farm life tradition, got interested in refrigeration and low temperature refrigeration. And Sam started developing his concepts for low temperature, particularly liquid nitrogen temperature refrigeration, when he was working prior to World War II with Dr. Keyes, and the thing Sam said, well, that wasn't thought of as an appropriate research activity. So I hid it and I worked on it at night. And I hid it over the day when the boss was there, and then I'd get it out. Sam had a commitment to making things that really produced some positive results. And I know one of his motivation was he thought about how hard his family and the people that were associated at his level in farming in those days, how hard they worked, and they seemed to get nowhere. And so he was just, I think his motivation was really, in a sense, striving to find a way for people that really worked hard to make a contribution rather than just, sort of walking a treadmill, so to speak, and not getting anywhere. I don't know. And so,
Smith, let me ask this question. Maybe off. You may not be aware of this. He spent some time at Wright Air Base in 1943-44 during World War II.
well, I'm not sure where he was doing the research, but I do know he worked on refrigeration equipment to produce liquid nitrogen in the combat zone instead of,
Liquid oxygen?
liquid oxygen,
Yeah.
Gaseous oxygen in the combat zone for breathing, aircraft breathing,
I think it had
rather than shipping it all from the U.S. And the tradition that I've heard was that if you go to certain South Pacific islands these days, they're paved with steel oxygen tanks from World War II because they shipped all the oxygen from U.S. in steel tanks, and they never sent any of them back. They didn't have. They wanted the ships to go fast and get back, so you didn't no time to reload. Just ship them back. Just get the ship back. And
we haven't been up too right. It's one of the trips that we're going to make. My wife and I, at least, and any others want to go. Because I know he spent some time there. In fact, Lena did some of the mechanical drawing for some of his designs or some of his
yes,
team.
I remember that now that you mentioned it. That she was the draftsman of the
she
family,
taught herself
and
drafting.
she put it together. But I do know that he struggled with the purification of the air that was going to be used to make the gaseous oxygen, pure gaseous oxygen. And
You had the air separation plant.
What?
Didn't you have the air separation plant in Building 41? I only saw remnants of the heat exchangers. Was there an air separation plant in Building 41?
No, definitely not. That
What were
was
those heat
before- That was
exchangers from?
before Building 41. Geez, because
But that was MIT.
it was MIT, the first nitrogen separation plant for, in fact, it was a nitrogen separation plant, not an oxygen separation plant. And it was built in, a compressor that ran it was in the basement of Building 3. And it was
This
there-
building.
And it was there long after that air compressor was the air compressor in that laboratory space, long after it was abandoned as a compressed gas source for the air separation experiment. And another compressor just like it was installed in Building 41. And it was there until I threw it out, I guess. And it kind of
Science and engineering research we do in the whole field of superconducting and solid-state physics and so forth. So he gave a tool or an instrument. So imagine, Galileo without his telescope, okay? You don't see, the rings of Saturn, you don't see Mars. And so in essence, his helium cryostat is one of those fundamental tools that allows you to create really unique physical environments for doing pioneering research that we feel the effects of every day, but are kind of invisible to us. So that camera that you're using, is a beneficiary of investigations that took advantage of this kind of early work. The world of the super cold is not just the domain of physicists or mechanical engineers. Chemical engineers for a long time have also been really interested in that kind of work because there's some very practical applications. So frozen food, for example, Bird's Eye that made its name with the frozen food movement. Most frozen food, when you do it yourself, you go out, you pick strawberries or fruit, and you put it in the freezer. It gets all mushy when you defrost it because the ice crystals form, then the ice expands, then you thaw it out, it contracts, and the water all gets droopy. And so that flash freezing with liquid nitrogen is one of the great innovations for all sorts of frozen food. That's why the strawberries and things you buy that are commercially frozen are so much better tasting. It's used for all kinds of recycling efforts. So when your car tires are dead, all of those are dumped into these gigantic vats that spray various supercooled gases, most often nitrogen, that freeze the rubber and then allow it to be pummeled and broken into shards and then recycled. The space shuttle, and in fact all of the American space program and the rockets are fueled with liquid hydrogen principally. And so these are just a couple of examples of the way industrial gas concerns, chemical engineering firms have translated this kind of esoteric knowledge that Professor Collins and others have contributed to into, again, practical, ordinary work in our lives. So MIT is a place filled with